But then I go to the machine shop. The machine shop says, I don't have any 3/4 inch bar. I can give you 1 inch bar, or I can give you half inch bar. So, of course I can say, well, go buy me 3/4 inch bar. Okay, I would say, fine, it'll take me about 3 months to get the 3/4 inch bar, and it'll cost you this much more. So you use the 1 inch bar. Now your real safety factor is better than your design, because you use the 1 inch. That's what I mean. What you actually build is based on what's available, not just on what you design. And you always go up in the safety factor. The safety factor is bigger than the design requirement. So remember these two numbers. As you work through your problems, I'm going to ask you for both this and this. If you look at the back of your book, there are tables of what you can actually buy. You cannot go out and buy a 0.78 inch diameter rod. You can buy a 1 inch rod. You can buy a 0.825 inch rod. You don't buy 0.78. So you will have to buy something else and then decide do you want to machine it down, which will cost you money, or just use the larger rod and accept that you get a better safety factor. Yeah.
Yeah, what about the exceptions where basically instead of like trying to work with what's available, we end up being forced to work on our own? Kind of like, I know it's kind of exaggerated, but Tony Stark was captured by the terrorists and then making an Iron Man suit.
Yeah, sometimes you have to build your own things. You build with what you've got. You still can't build with, you typically cannot get just what you design. You will always look at what you've got. So you have to build that.
So this max allowable stress is something you define, right? So it's what you tell the user.
Right. So this is where you get into issues where you design the thing. Classic problem is tools, right? So you can buy a bar stool. You go to any furniture store, you can buy a bar stool. These bar stools are basically long columns with a seat on the top. And you assume that the person who's sitting on it is a certain weight. And you don't write it down. And you buy the bar stool and you give it to somebody. And then they put the bar stool up. And people get fatter and fatter. It might even be the same person sitting on that stool 20 years later. And the stool will collapse. The loads change. Okay. Actually, the way stools collapse is really interesting. If you've ever seen a video of this is really a fun thing. Okay. Oh. And remember that NS is always greater than S. All right. And the last thing I want to talk about is codes and standards. So as professional engineers, you cannot design anything you like. Your professional societies and government have agreed that there are certain things that are allowed and certain things that are not. You have to build to those standards. So the distinction in a code and a standard, right? Either of them is an agreed upon specification for something. So the community agrees that we shall do this. That's what a code and standard is. But a code is an agreed upon specification for a process. So the community says this is how we shall do something. Whereas a standard is an agreed upon specification for a thing. So you might have a code for how you build a helmet, and you might have a standard for a helmet. And you are required, if you are a seller of helmets or a designer of helmets, to meet the codes and standards. Okay? So let's actually I have a few examples. So one thing to remember about these codes and standards, they actually do carry the force of law. So if there's a code that the community has agreed to, and you make something that does not meet that code, you are legally liable. The interesting thing about the United States law, US law says you are liable if a problem occurs. It doesn't matter whether you could have known that a problem occurs. It doesn't matter if you didn't know about it. It doesn't matter if you couldn't have known about it. If the problem occurs, you are liable. European law is a little different. European law says if you couldn't have known about it, then you are not liable. American law is it's your product, it's your problem. So, liability is there. Alright, let's see if we can go. I'm just going to show you a few codes and standards, and maybe give you some examples. The typical places where you find codes and standards: ASME, the American Society of Mechanical Engineers; ANSI, the American National Standards Institute; ASTM, the American Society for Testing and Materials; OSHA, the Office of Safety and Health. So these kinds of places. Why do we use codes and standards? Let me write those down for a minute. So one is conformity. So at least we all agree on the same thing. So an example of conformity is you guys buy Tylenol or acetaminophen, you have a headache, you decide to take it. So 375 milligram tablet, you take 2. Why do you take 2? You could have taken 3, you could have taken 4. You actually could take 5, but you take 2. That's a dosage. That's a code. A bunch of people got together and agreed that 2 would be acceptable. If you take 3, you're at fault. Right? So this is what conformity means. We all agree we're doing the same thing. So when we take the dose of acetaminophen, if you go into the hospital and you say you're taking a dose, well, they know what you're doing. Okay. The second is interoperability. So if you and I both build products to the same code, I can take your product and it will fit my product. I can buy your gear and my belt, and they will work. Or your gear and my gear. Your sprocket and my belt. They will work. Because they were built to the same code. For safety. So safety codes are very common. Boilers, for example. This country used to kill about 100,000 people a year in boiler accidents. Now we kill nearly 0. That's cool. Environmental things. So your slow leak, fast leak, that's actually environmental. This last one is kind of strange, but you have to know about it. Documentation. So there are codes that say how you document your results. There are codes that say how you document your design. So that I'm NASA, I can buy a part from Morton Tire Co, and I know exactly what it is. Okay, so with those in mind, let's look at a few codes and standards. Here they come. So I'm going to show you a bunch of codes and standards. You can go find these online at any time. We'll start with ASME. So all of you, well, most of you are mechanical engineers. You ought to be a member of the American Society of Mechanical Engineers. That is the professional society that defines how you work. So here's an example. This is a rope. So you're buying wire rope. It's a hoist actually for lifting something. There's a standard for that. You can actually buy the standard if you like. ASME sells the standards. There's a standard number. You can go look at it. It tells you, well, if you're buying that standard, well, you might also be interested in these related standards. These are things you would use. Let's go ANSI. So this is the American National Standards Institute. And it has standards for all these different things. So let's go to standards and publications. We can look for a standard for something in particular. Let's say, well, right. So you can choose any one of these and go look at it. In the interest of time, I won't run through all of them. Here's the ASTM. ASTM is usually related to materials. So if you buy a bar of steel, it will be specified by an ASTM standard. If you buy 6061 T6 aluminum, that is defined by an ASTM standard. That's why we know that whether you buy it from this company or that company, you're going to get the same thing. OSHA defines its own standards for a lot of things, get much more legal issues from OSHA. So OSHA standards are absolutely legally binding. ASTM, ASME, ANSI standards may be legally binding. That depends on how good your lawyer is, or how good your other side's lawyer is. So if the lawyer can prove that pretty much everybody follows the standards, then it's legally binding. If the lawyer says, well, there's a brand new standard, it just came out, only 15% of the industry is doing it. So, let's look at this one. So helmets. Let's say you are a company that wants to make helmets. These are actually bike helmets, I think. Well, this is general helmets. This is the Consumer Product Safety Commission, CPSC. They define what kinds of helmets you can make. How those helmets should be built. In fact, if you come down here, if you choose, if you choose the kind of activity, it'll tell you what kind of helmet you want, and it'll tell you which standard you have to use. You cannot just go build your own helmet, or you can, but you can't use it. You can't sell it. You have to meet those standards. Okay. So that's how quality standards are. So lots of them, it's up to you to figure out which ones apply to your particular product. All right, so let's go back to getting our mechanics there. So there's another company, another agency's standards that you might find interesting. That's NTSB, National Transportation Safety Board. So if you get a chance to go take a look at NTSB facilities in Virginia, they have what they recovered of the TWA flight that crashed off LaGuardia. So they have to remain to that flight, and we'll see exactly how it fails. We'll see if we can wait. All right, so let me change tacks here, and we're done with the design components. Let's go to mechanics. Let's talk about stress. Let me start by defining how you should think about these problems. So there are 4 parts to any problem that we look at. So the idea is you start with design considerations, and design considerations converted to a mechanics problem. Now each mechanics problem you have to look at in terms of these 4 parts. The first part is basically the way the problem is set up. So this is the conceptual part. This is the string of words that define the problem. So it says, well, a circular cylindrical rod that's spanning a force. Right? The second part is geometry. How long is it? What's the diameter? What's the shape? What are the corners? What are the dimensions? What are the tolerances? That's the geometry. The third part is loading. What kind of forces do they apply? Tension, torsion, bending. Where are the forces applied? At what distances? How large are the forces? And the fourth part is material. What material is it made of? What are the properties of the material? Every problem in mechanics is those 4 parts. Every time you want to solve a problem, that's what you will look at. Do I know these 4? If there are things you don't know, you need to ask somebody because the problem is not well defined. So you need to know those 4 every time. And that's how you work a problem through. You start by writing down that conceptual part might be a drawing that says this is what it looks like. The geometry part will be putting down the dimensions in the drawing. These are the lengths and the sizes. The loading part will be putting down the forces and defining what those are. Then the material will be saying these properties of the material. Once you have those four, it's I think you guys know most of this, so let me just talk about loading. There are different types of loading to think about. Tension, which you guys have done. Torsion, which you guys have done. Bending, which you've done. Not very well. Pressure. And then, of course, various combined loading. Combinations of all. And then we have special cases at the bottom that we call plane states. So we are going to make sure you know how to solve problems of all those types. Plane states are problems where the thing is either very thin or very thick. If the thing you're looking at is very thin, then it's a plane stress problem. The stress is in the perpendicular direction of the map. If it's very thick, it's a plane strain problem. The strains in the thick direction of the map. So these are the basic problems. Okay. I'll do my 2-minute review. Oh, I should say first. Bending, I don't have enough time to cover bending in as much depth as I would like. So I've asked Amy to teach bending tomorrow in the recitation section. It's from 8 to 9:30 in, no, it's Chapel 3, in Chapel 3. And she's going to cover shear force diagrams, bending moment diagrams, how to calculate the bending stresses, all of that. I'm just going to give you a quick overview, but I'm assuming that you guys will go to that recitation. Okay, let's walk through the pieces of all of these. So tension, this is very easy. Imagine I've got something like this. Let's put as a tension. Or let's call this dimension W. Call this L0. This is W0. The cross-section area of this thing we call A0. Let's assume it's a square. So this is also W0, the square cross-section. So then your A0 is just W0 squared, right? I apply a force F on the ends. I'll call this direction the x direction. Then my stress along the x direction, sigma x, is the force in that direction divided by A0, right? This is the stress. My strain along the x direction is the new length, so L0 goes to L0 plus delta L, becomes a new length, becomes longer. Epsilon x is delta L over L0. This is the strain in that direction. Now if I think of the width of this thing, the width will actually decrease, it will become thinner. When I make it longer this way, it shrinks this way. So that's epsilon y. It's the change in strain in the y direction. That's going to be the change in the width divided by W0. In a simple tension problem, you have one stress but two strains. Actually, three strains because you also have an epsilon. The relation between epsilon y and epsilon x. Well, let's actually write these down. So epsilon y is usually minus mu epsilon x. Nu is Poisson's ratio. You guys have heard of Poisson's ratio, right? The relation between sigma and E is sigma is equal to E, so sigma x is equal to E epsilon x. Sigma is the stress, epsilon x is the strain in the x direction, E is the Young's modulus. Okay? So, conceptual problem, geometry, load, material. Okay, that's tension. Much time, and let's move very quickly on to knowledge. some kind of a shaft. You have a torque T that's applied. It has a length which is L, L0. It has a radius which is R. Your shear stress here is TR over J. You guys have seen this last year. J is the polar moment of inertia. It closes out to the force. You have a shear strain gamma. Basically the thing twists. And the amount it twists is determined by G, L, you guys remember? Have a break, please. The shear strain. What is it about? So G theta over L. Theta is how much you actually twist. The shear strain is the change in angle. What amounts to G theta over L. And you can run through the rest of it. You guys have done this before, I think, so I'm not going to do that. Okay. Is G theta over L? Or theta over L? Any takers? Okay. You guys can pull this up. All right. Last one we want to look at is bending. Stop. And leave it to Amy to finish up. Bending. It looks exactly like that. I've got some kind of a wire or a beam. Eyes up?
Yes, sir.
Okay, thank you. That's what bending looks like.